All right. So I posted programming assignment 1 a couple of days ago, I think. And so let's take a quick look at that. And then I want to go over the midterm. And then take any general questions, and then we're going to go back to talking about mathematical induction. Let's start with PA1. Let me see. All right, programming assignment 1. So this I've got marked as due November 10th. So you've got a couple of weeks to work on this. I don't know when I'm going to post programming assignment 2, because I just got this up. But this is a chance to play around with some of the stuff we did last unit related to number theory. And so we're mainly playing with divisibility and factors. And the code you submit should be plain old generic C code, and it should be code that runs on the Linux server. So if you already are taking 224, you've got an account on the Linux server. If you're in 215 but not on 224, send me an email. I'll set up an account, let you know that it's ready to go. And your code has to run on the server here, so if you develop it in some other environment but it doesn't work for me, that'll be a problem. And so basically you're going to write a program that asks the user to enter a number and then does some analysis on it. And the analysis should be the following 4 things. First, I want to see a list of all the numbers that divide your number n. And you should include the number 1. So if I type the number 8, you should print out 1, 2, and 4. Those are all the things that divide 8. And then say either it's prime or composite. So it's prime if the only factor between 1 and n minus 1 is 1. If there's any other factors, then it's composite. And then calculate the sum of all those factors, and then print out something that we call the mood. If the sum of the factors is smaller than n, you can say that number is sad. If it's bigger than n, it's happy, and if it's equal to n, it's perfect. And and then your program should exit. So I run your program, it asks for a number, I type in a number, and it says the factors are colon, the number is prime or composite, the sum of the factors is this, and then the number is sad, happy, or perfect. And it's got to be written in C, should compile with just a plain GCC switch, possibly with LM if you're using the square root function. And you should upload the .c file to Canvas. And if you're breaking your program into multiple pieces, then you'll want to create a tar file and upload the tar file. If you don't know how to do that, just put it all in one file and upload that .c file. And there's a sample executable under /temp that you can use to explore what this program should do. So let's hop in there. And if you do /temp/215 PA1, it says enter a number. So somebody give me your favorite number.
23.
23. So the factors are 1. 23 is prime, the sum of all factors is 1, and 23 is sad. Prime numbers are always sad. Alright, someone give me another number.
Say 100.
So the factors are 1, 2, 4, 5, 10, 20, 25, 50. 100 is composite. The sum of the factors is 117, which means 100 is happy. There are perfect numbers. They're pretty rare, but 28 is perfect, for example. If you add up the factors, you get exactly 28. So that's the whole PA1. And basically to do this, you need to be able to know if something's a factor of a number, and you can do that with the modulo function. So if you say a%b, that will tell you what the remainder is when a is divided by b. And so if n%f is equal to 0, then f is a factor of n. So make a loop from 1 to n minus 1 and, loop over f, for example, and for each f, see if n%f is equal to 0. If it is, it's a factor, which means you can do the following. You can print it out since you're printing a list first, and you can add it to a running sum. When you're done, if the sum is equal to 1, you have a prime number, because it means the only factor you found was 1, and 1 will always be a factor. And then you can compare the sum to n, and that will tell you if it's happy, sad, or perfect. You do not need error checking in this, so you can assume the user is not a cat going crazy on your keyboard, and that they're typing in an integer. And they'll type in a positive integer, so they won't type in 0 or negative. So yeah, assume the behavior is the user is well behaved.
But would error checking hurt?
Wouldn't hurt. But unlike 224, all I really care about is the behavior of the function and making sure it's written in C. So if it does the right thing, you're good to go. All right, go ahead and let's do an attendance check, not an appendix check. Let me know you're here, not whether you have an appendix. And some things to play with on this. If you put in a factorial, that should be a really, really happy number, right? The sum of the factors should be much bigger than the number itself. If you put in a prime, that's always going to be a really sad number because the sum will just be 1. And then perfect numbers are that sweet spot. So, and you could, if you put this in a function, you could run it inside a loop and you could look for perfect numbers, or you could count how many numbers are happy, sad, and perfect, say between 0 and 1,000,000, and maybe discover some interesting things like that. But that's not required. All right, any other questions on PA1?
When is it due?
Let's see. November 10th, 8 a.m.
Okay.
And you can upload a C file, a tar file.
If we use multiple files, like multiple .o files, just put it all in a tar bar?
Put it all in the tar file or a tar ball, your choice. And we're going to talk about tar probably tomorrow. Well, not tomorrow, but Monday in 224. All right, let me bring up my notes.
So, for the mood of that, a case or a switch case, right, would be probably the best way to go for that one.
Switches don't really work well with positive, negative. Switches really work well with very specific values. So I would probably just do some if statements. If the sum is less than n, then print it sad. If the sum is bigger than n, print it's happy, and so on.
Okay. And
All
then
that
just
such
always
statements
assume
really
that
are
it's-
anyway. Syntactical sugar.
Try that again.
We just assume that it's going to be one of those, right? Like, we're not going to worry about errors or anything like that.
Yeah, yeah.
Okay.
And every number will be either happy, sad, or perfect.
I guess it would have to be one.
Yeah.
That's true.
All right, and we are wrapping up week 6 here, so we are flying through. Let me tell you where we're going from here. So I'm going to talk about the midterm next, and then we're going to do more mathematical induction, and we may not finish induction until Monday, which is okay. And then Wednesday I'll post some homeworks related to induction. So we got a week break from homework this week. So after this, I want to talk about counting. That's our next unit. And that's going to take us into a lot of non-obvious things that we can do. And we'll end with talking about permutations and combinations. So lots of good stuff in there. I'll talk a little bit about recurrence relations, which will tie into CSE215 in winter. I may talk about trees and graph theory. Probably more about graph theory than trees. So just other ways of organizing and using data inside a computer. And we really only have 4 full weeks of school left because we lose about a week over Thanksgiving. So, so we'll talk about graph theory, maybe some trees, and then talk about automata theory and formal languages and grammars. And then we'll probably wrap up talking about state machines and Turing machines and models of computation, and some open problems related to all of that, and so on. So we're well past halfway in the course as far as material and as far as time, obviously. So on the midterm, there were a number of different things that happened. One of them being that a lot of people lost a lot of points on the set theory problem. And I kind of intended that to be, kind of a way to ease into the exam and get a bunch of points in the beginning. But I think a lot of people kind of forgot about set theory because it was so long ago, right? And so people ran into difficulties with that, which I hadn't planned on happening. But that was one thing that pulled some people's scores down. And as I posted in an announcement, if your score on the midterm seemed low to you, I don't want you to get discouraged by that, but you do want to take that into consideration and maybe make some adjustments going forward through the rest of the course. So proofs are definitely challenging, right? And one of the goals in this course is to get better at doing proofs. But if you finish the course and you're still not able to write a perfect proof, that's not a problem, right? That's not going to stop you from being successful in computer science or anything else in life, unless you get a job as a proof writer or something. So as much as you can get of this material, right? That's good. And I graded the exams, based on how many points the problems are worth. But if you came out with a really low score in your assessment of it, don't panic over that, right? Come by Zoom and let's talk, and let's make sure that if there was some fundamental concept that you were missing that cost you a bunch of points again and again and again, let's nail that down and just figure out what it is. But a lot of times, like I say, it's sort of a question of just kind of getting nickel and dimed. Like, I forgot what a power set was, I forgot what an intersection was, I couldn't remember the name of this theorem, I proved the converse instead of the forward. Well, you might have lost half your points just there with things that were relatively simple mistakes, but compounded into large numbers of points. So if you're worried about your grade, just come by and let's talk. and let's go over your exam and take a look at each question and make sure that when we get to the final you can do these things. So reading user's input for PA1, since the user is well behaved, you can go ahead and use scanf if you want. Just don't slip up and start using that in 222 or 224. But you know, there's nothing wrong with doing fgets and scanf. That's another chance to practice that. But yeah, if you use scanf, I'm not gonna take off points for that for 215. All right, so let me pull up the midterm. Most people got the honor statement correct. A few people submitted it late. I'll be more clear about this on the final, but really what you want to do is at the top of the thing that you're turning in, write the word honor statement followed by your name, right? So that it's part of the thing that you're turning in. But I'll make that more clear on the final. And so first question was set theory. So a pair of sets, A and B, and let me write these down and then I'll move that out of the way. So A is X, Y, Z, and B is T, W, X, Z. All right, so first question, find the union. And the union just means the collection of all things that belong to either set. And it's also like a logical OR operation. List an element in this union if it belongs to A or it belongs to B. So X belongs to A, Y belongs to B, to A, Z belongs to A, T belongs to B, and W belongs to B. So there's the union. And nobody listed X or Z twice, which is great, thank you. Because we don't list elements more than once in a set. So there's the union. The intersection is the set of things that are contained in both A and B. So it's a logical AND. List an element if it's in A and it's in B. And there's two of those. There's the letter X and there's the letter Z. A subtract B, this is the complement of B in A. It's the set of all things in A that are not in B. So it's always going to be a subset of A. And one way to do this is write the elements of A and then throw away anything in here that you find in B. Well, we find an X and we find a Z, and so this is just the set Y. So we sometimes call this subtraction, but it's a little weird because, you know, subtracting the T doesn't do anything. It says if there was a T here, we would get rid of it because of that. But having the T in B doesn't do anything by itself. We don't get like a negative T or something. So A take away B is just the set Y. And then the power set of A intersect B. So this is itself a set. And each element of this set is a subset of, in this case, that. So the possible subsets are the singleton X, the singleton Y, the set itself, sorry, Z, the set itself, and the empty set. And then finally A union B, take away B. Well, A union B is this thing. Take away B, which is TWXZ. And so start with this set and throw away anything you find here. Well, that's going to throw away the X and the Z and the T and the W. And this will just leave you with Y.
And I way oversimplified that. I should have wrote it out. I just basically took A, U, and B, and then said, oh, we'll take B away, it's just A.
Oh, okay.
Obviously, I saw that as soon as we started going through, I was going, that's what I got wrong.
Okay.
Such a easy thing to get right, and next time I'll have to write it out a little more thorough.
Well, on the other side of that coin, right? Sometimes people overcomplicate things, and I didn't see it on this exam, but sometimes, you know, I'll ask for the power set of A intersect B, and I'll get like a whole page, and people will start, you know, naming rules of logic and things like that, and so it can go both ways sometimes. All right, question 2 was matching. No, question 2 was the short calculations. So GCD of 126 and 220. So this is Euclid's algorithm. 220 equals 1 times 126 plus, I think it's 94. 126 equals 1 times 94 plus 32. I did that on my fingers. 94 equals 2 times 32 is 64 plus 30. 32 equals 1 times 30 plus 2. And then 30 equals 15 times 2 plus 0. And so this is your GCD. And you can check that if you want. You can make sure it is a common denominator by dividing both sides by 2. 126 over 2 is 63. 220 over 2 is 110. And then if you, so it is a common divisor. Is it the greatest common divisor? Well, you could see if these things have any divisors in common. And you can do that by factoring. This is 3 times 3 is 9, times 7 is 63. This is 2 times 5 times 11. And there's no prime factors in common, so there can't be any factors in common at all. So 2 is the GCD there. All right, the next question was using modular exponentiation to calculate 9 to the 131st mod 7. And modular exponentiation is a very specific algorithm. And it goes in a series of steps. The first step is to write this thing raised to different powers where each power is a power of 2. So 9 to the first is just congruent to 2, or you could leave it as 9. 9 squared will be congruent to 4. Now we jump to 9 to the 4th. This will be 16, which is 2 more than 14, so this is 2. And we've got our pattern. So I'm going to do this up to 128.
So, for modular exponentiation, is it once you get into a pattern, you pretty much stay in that pattern?
Mm-hmm.
For most cases?
Since each step I'm squaring the answer from the previous step, if this is the same as a previous step's answer, right, that matches that. I know when I square this, I'm going to get the same thing as when I squared that. And your pattern may not be just 2 numbers. It could be a cycle. It could be, 2, 4, 7, 3, 2, 4, 7, 3. But eventually it will repeat. And then at that point, that's...
Yeah, usually, I'm pretty sure in the homework in this one, it went back and forth between like 2 numbers.
Mm-hmm.
So I was curious if that was the case. So there can be different patterns, just
Yeah, and if you use a larger modulus, you're probably going to repeat, but with a longer cycle. For example, if I did 6, right, I think that would um, let's see what this does. 6 to the first is congruent to 6. 6 squared is 36, which is, no, that's one more. All right, so that's just going to be 1 all the time. Interesting. But yeah, in general, it could be any length cycle. So that's the first part, is finding these powers of the number you're finding the exponent of. And then we don't just sort of try to put these together to come up with 131. We write 131 as a sum of powers of 2. And then we use the law of exponents to say this. Right, so this 131 is equal to this sum, so 9 to the 131 is equal to this product. And since we've calculated each of these modulo 7, we can say this is congruent to 4 times 4 times 2. And then you do the calculations. This is 16 times 2, which is 32, which is 4 more than 28. And the only minor issue I saw in multiple versions of this was some people, you know, got up to 64 and then said, well, 64 and 32 is 96, and I'll add another 16 and do something, and I'll get up to this, and I'll do this 5 times, and that'll get me up to 131. You can do that, you'll get the correct answer, but that's a hard thing to code into an algorithm, right? Whereas this is very, very automatic, because doing this is just looking at 131 in binary, right? If I look at 131 in binary, it looks like that. Well, that's 1, 2, and 128.
I just kind of found a weird pattern from what you did. I don't know if it's a theorem. I don't think we talked about it. But if you take n mod n plus 1, it's coming out as 1 pretty much every, well, from what I've done.
So if you do n mod n plus 1, n will actually turn out to be congruent to minus 1 mod n plus 1. Because n minus minus 1 is n plus 1, and that's divisible by n plus 1. And so if n is congruent to minus 1, n squared is congruent to minus 1 squared, which will just be congruent to 1. And then you're off and running, everything's going to be 1.
Yeah,
So yeah, you discovered a valid theorem.
it's interesting.
Yeah. And these negatives are fun. So if you look at other videos online or Stack Overflow or things like that, for any of the material in this course, right, there's a good chance you're going to encounter things that may be called the same as what we're describing, but are different. For example, natural numbers, do they include 0 or do they exclude 0? If you come across, you know, a different technique that's called modular exponentiation, that's great, but if I ask you to do modular exponentiation or to use Fermat's Little theorem on a test, you got to do it the way that we're talking about it in class. You're not required or expected to, you know, learn this stuff from outside sources, but you can always ask, right? So if you are doing your own looking around online, you find something different that's called modular exponentiation, right? Go ahead and ask in class, or come by office hours and say, hey, you know, I found this simpler way to do this that's called modular exponentiation. Can I do this? Right? And this you know, like when you calculate 2's complement in engineering 250, there's different ways to do that. Um, and some teachers will let you do that. Some teachers will want to see it done a very particular way. So you can always ask for clarification. All right, and then third question was find a number that's relatively prime to 100, meaning the greatest common divisor of x and 100 should be equal to 1. And there's a lot of ways that you can do this. If x is any prime numbers have no factors other than themselves and 1. So for example, if I just said 3 and 100, there's no common divisor except 1. Or if I did 13 or 31 or 17 or 97 or any other prime, right? Or 101. You're also pretty safe going one more or less than this number, so 99 and 100 aren't going to share a factor. And one person did 1, and yeah, the greatest common divisor of 1 and 100 is 1. Because the only divisor of this is 1. Only positive divisor. So not a lot of trouble there. And then the last one, which I think everybody got mostly right, was using Fermat's little theorem to compute 7 to the 362 mod 37. And FLT tells us that, you know, if we take 7 and we raise it to the 7 minus 1, raise it to the 37 minus 1, 7 to the 36th will be congruent to 1 mod 37. That's as long as 7 is not a multiple of 37, which it isn't. Well, this is a nice fact, because if I take this and I raise it to the 10th, I'll just get 1 to the 10th, which will still be 1. But 7 to the 36th raised to the 10th, that's 7 to the 360th. I'm trying to find 7 to the 362nd. Well, I just leapfrogged through my first 360 steps. If I know 7 to the 360th is 1, I can multiply by 7 once more and say that's congruent to 7. And then this will be congruent to 7 times 7, which is 49, which is 12 more than 37. So there's your answer. All right, part 3. So this was looking at laws of logic and matching them. And I didn't mean for one of these to be kind of tricky, but it ended up being kind of tricky. All fish swim, I swim, therefore I am a fish. So logic should tell you that that's probably a fallacy of some kind. Because it could be true that all fish swim, it's also true that I swim, but I'm not a fish as far as I know. So this is some kind of fallacy. All fish swim. Well, if we put that in the form of a conditional statement, it looks like if you are a fish, then you swim. So if you're a fish, then you swim. So this is the hypothesis. This is the conclusion. And in this statement, we're saying I swim. So we are affirming the conclusion and then trying to use that to support the hypothesis. So this is the fallacy of affirming the conclusion. Right, so that's good old B. All right, the second one, if I study for class, if I study, then I pass. I did not pass. Therefore, I did not study. All right, that's what that theorem is stating. This is classic indirect reasoning. If we imagine that S is the proposition that I study and P is the proposition that I pass, we're saying S implies P, not P, therefore not S. Okay, that's indirect reasoning. Some people said contrapositive for this. And we can use the contrapositive to prove this, but it takes a few steps. To prove this using contrapositive, we would say S implies P, not P. We would say, since S implies P, we can use the contrapositive of this statement and assert that not P implies not S. And then we could use detachment. Oh, you're right. If this is S and P, S implies P, not P, therefore not S. You could say S implies P, not P, those are the two hypotheses. We could apply the contrapositive to this and say, since this is true, this is also true. Not P implies not S. And then you could take these two, combine them using detachment, and conclude not S. So you can use the contrapositive plus detachment to get from here down to S. But as an entity by itself, this is an example of indirect reasoning. All right, if one studies for class, they pass. You studied for class, therefore you will pass. So if you study for class, you will pass. You study for class, therefore you pass. That's detachment or direct reasoning. So C would be F. All right. D, if it's sunny, I go for a run. If I go for a run, I'll get hungry. Therefore, if it's sunny, I will get hungry. That's the good old chain rule. All right, this implies that. That implies this other thing, so this implies that other thing. And then the last one, I'm going to study computer science or art. I'm not studying computer science, therefore I'm studying art. So if C is the proposition, I'm studying computer science. A is the proposition, I'm studying art. This first statement says C or A. The second statement, I'm not studying computer science, says not C. And the conclusion is I'm studying art A. And that's disjunctive simplification. All right, and then the two proofs. So this first proof, by and large, people did really well on this. So let me write this down. D, B implies A, B or C. D implies not C. And all of that implies A. So you look at this, well, you're trying to prove A. There's only one statement that mentions A, that's this, so I'm going to have to prove B. The only other statement that mentions B is this one, and this says B or C. The only way I can get from here to B is if C turns out to be false. And hey, there's a statement that concludes C is false. What do I need for that? I need D. Hey, I've got D. So that's kind of the pre-game, you know, stare at this, see if there's something that might get you where you're trying to go, and then start writing it up. So I could start off with, you know, D implies not C. That's a hypothesis. D is a hypothesis, and so I get not C. That's detachment. And I know B or C. That's a hypothesis. And good old disjunctive simplification. B or C has to be true. C is false. Therefore, B has to be true. And let me start numbering these. So this was detachment using 1 and 2. This is disjunctive simplification using 3 and 4. And then I know B implies A. That's a hypothesis. And since B is true, this gives me A. This is detachment using 5 and 6. And that's your QED. If you did an indirect proof, you would assume not A. That's the negation of conclusion. And B implies A is a hypothesis. Well, if B implies A and A is false, that gives us not B. That's indirect reasoning. And we're told B or C. That's a hypothesis. So again, disjunctive simplification tells us C has to be true. Because B or C has to be true, and we just showed B was false. And D implies not C. That's a hypothesis, but we've just shown that this conclusion is false, and so that tells us D must be false. That's indirect reasoning. But we're also told that D is true. That's a hypothesis, and there's your contradiction. Therefore, A must be true. That's the end of the proof.
Just out of curiosity, I've always found the direct proofs to be easier, just the way I think about it. Is there any benefit to the indirect way?
I think it's like KVL, KCL. I think depending on how we're wired and how we think about things, there may be one approach that feels preferential. And I think for most people, direct proofs feel more natural. Well, I mean, they're direct, right? But there are some people who just kind of naturally gravitate to this line of thought, thinking in terms of contradiction, trying to argue to a contradiction. I don't think there's any particular benefit one way or another, as long as it gets you. Yeah. And there's some questions, like these questions with squares and odds and evens, where it feels really hard sometimes to find a direct proof, whereas the indirect pops out right away. It's difficult to do a direct proof that the square root of 2 is irrational, whereas the indirect proof, right, finding a contradiction if we write square root of 2 as a over b is more doable. So, but it's an interesting question. Why two different approaches that get you to the same place sometimes feel so different and have totally different levels of difficulty. All right, and then the last question was another proof, and this was a proof about evens and odds. And the question was, if n is odd, let's prove that 5n is also odd. And this is, one of those cases where we got to be really clear what direction we're moving. If n is odd, then 5n is odd. And so I'm going to, right at the top of my thing, I'm going to say what I'm trying to do. Prove if n is odd, then 5n is odd. All right, so how do we do this? We only have one hypothesis, which is that n is odd, so let's begin with that. N is odd. That's a hypothesis. And about the only thing we can do with that is turn it into an equivalent statement, which is there exists some integer k such that n equals 2k plus 1. And that's what it means when we say n is odd. All right, at this point, everybody started trying to do something similar, but in some different ways. Our goal is to ultimately be able to write 5n equals 2 times something plus 1. Right? As soon as we do this, we can say, therefore, 5n is odd. Right? As long as this is an integer, and we can write 5 as 2 times an integer plus 1, we're done. So this is what we're really trying to get to. We're trying to do some algebra and write 5n as twice an integer plus 1. So I'm going to start off by saying 5n and the only thing I can do is substitute 2k plus 1 for n. So this is 5 times 2k plus 1, which is 10k plus 5. And now we need to write this as 2 times something plus 1. And so this takes some trial and error, but no, I can divide this by 2, but I can't divide that by 2, but I've got this extra plus 1 on the end. So I could write this as 10k plus 4 plus 1. And now I've got my plus 1 part, and I need to write this as 2 times an integer, and that turns out to work really well because 10 is divisible by 2 and 4 is divisible by 2. And so now we've without doing anything about evens and odds or anything else, we've just algebraically shown 5n is equal to 2 times this plus 1. And then we could, so this is all algebra, and we could say, you know, 5n is odd, and this is definition of odd, and 5k plus 2 is an integer, and that's what we're trying to show. So that's where we can end our proof. And things that can go awry here are sort of losing sight of the structure here and just starting to write things like you know, 10k plus 5, 10k plus 4 plus 1, 2 times 5k plus 2 plus 1. Right? These are not propositions. Right, so we need to make sure that we're writing declarative statements. Here my proposition is this is equal to this, which is equal to that, which is equal to that, which is equal to that. Right, that's a big long prop.
That's just going to be one step then.
So that you could break it into multiple steps, right? I could make each of these a proposition where I said 5n equals this and 5n equals that. Right? Or I can, you know, string them all along and say a proposition that all 5 of these things are equal to each other, or whatever. But the important thing is make sure that you're writing propositions, and make sure that before you say QED, your last statement is 5n is odd, because that's what you're trying to show. And make sure that before you write this, you've shown 5n is twice an integer plus 1. And if I get down to this step, and then I say, you know, 10k plus 4 equals 2 times 5k plus 2, and I don't have this, I'm not ready to declare that 5n is odd. Right? My last statement is 10k plus 4 is 2 times an integer. Well, that's part of what I need to do, but before I can say 5n is odd, I really need to state 5n is equal to 2 times an integer plus 1. So I would need to go back and substitute this in for here and write that out so that I have a statement which clearly shows 5n is 2 times something plus 1. And then I can say, therefore 5n is odd. And then there's other pitfalls that we can run into, such as you know, at some point along the way, mistakenly writing 5n equals 2 times j plus 1. Well, we can do this if we know that 5n is odd, but if we don't know that, we can't write this. Right? We can only state that 5n is twice an integer plus 1 if we know 5n is odd. And if we haven't already proven that, then this does not follow. But sometimes I'll see proofs where somebody will, you know, write this as like their third proposition and then do some other stuff and then conclude 5n is odd. And that's circular, right? As soon as I've written this, I've asserted that 5n is odd. And so what I've really proven is if 5n is odd, then 5n is odd. And this is always true. If p, then p. But that does not prove that P is true. Let's see.
Yeah, that definitely helps a lot.
Okay, cool. Let's see. Question A, fallacy of affirming the conclusion. P and Q are true, and P implies Q should be true, but I am a fish is false. So the hypothesis is false. So these fallacies, the names are potentially ambiguous, and it only took me about 2 years of teaching this course to finally remember which is which. But P implies Q, Q, therefore P. That's one fallacy. P implies Q, not P, therefore not Q. That's another fallacy. So question 3A, which was, if you're a fish, you swim, I swim, therefore I'm a fish. That's definitely this situation. If P, then Q, Q, therefore P. And the naming of these, they're just names that were given to these, and this one is just called, fallacy of affirming the conclusion, and this is fallacy of denying the hypothesis. And they can feel ambiguous because, in this case the hypothesis, turns out to be false, but we don't call it that. It's just called fallacy of affirming the conclusion. So I think of it as what is the thing that you're doing before you get to the fallacy, right? In this case, this is hypothesis, conclusion. I'm saying the conclusion is true, and then I'm getting to a fallacy. In this case, I'm saying the hypothesis is false, and then I'm getting to my contradiction, or my fallacy. So yeah, I think you're thinking about it right. All right, other questions on the midterm? Oh, interesting. All right, let's take a 5-minute break, and then we'll come back. We'll start talking about mathematical induction. And let me think about what someone's asking in chat. So let's do a 5-minute break, and we'll come back at 1:30. All right, welcome back.
Yeah, sorry about the confusion I was explaining about. Basically, what I was trying to explain is I was using a truth table idea
Mm-hmm.
to kind of determine the fallacy, because if P and Q are true, then the conclusion then P then Q would have to also be true.
Okay.
And so, and because for 3A is false, I took in my mind that, well, that's a fallacy since it doesn't satisfy the truth table. So that's why I put the fallacy of conclusion.
Ah, okay.
Weird. Somehow I got the right answer.
Yeah.
I don't think I was speaking down right.
Well, that's an interesting way to think about it. So this fallacy looks like this. And if we think of it in terms of the truth table for the conditional, it looks like this. So 4 possibilities. And in most cases, the conditional turns out to be true. All right. So what does this statement tell us? It tells us P implies Q must be true. So we're only interested in these rows and this row. We're not going to consider this row.
Okay.
This tells us that Q is true, which means we're interested in any of these cases where P implies Q is true, meaning we circle it, and also Q is true. So we're interested in this case, but also this case. And so these two conditions can be true either here or here. Well, in this case, P is false. In this case, P is true. And so looking at the truth table, there's 2 possible values for P where both of these statements could be true. This fallacy is claiming, hey, if these are true, P has to be true, which could be the case. We could be down here, but we could also be in the second row, where P is false, but Q is true, and P implies Q is true. So that's a cool truth table way to sort of see why it's a fallacy.
Yeah, that was my idea.
I like that.
But I still find it weird that, like, if we let P be the preposition for all fish swim, and Q for I swim, then the conclusion, the fallacy conclusion would have said, like, therefore all fish swim. It's kind of, you see what I mean? Like, it's like, the conclusion, I am a fish, does that equal the hypothesis for P when it says all fish swim?
But this is a different setup, I think. So if we let B be the proposition, all fish swim, and let Q be the proposition, I swim, right? This is not saying P implies Q, which is saying if all fish swim, then I swim. That's a very different proposition from either, either of our original statements.
Interesting.
Yeah. All right. Well, mathematical induction. We began talking about this a while back. And we did a motivating example, or what was supposed to be a motivating example with De Morgan's theorem. And did I do a second example? I can't remember what it was. We did the sum of consecutive integers, right? Did we do an induction proof on the sum of consecutive integers?
I don't think so. Yeah, we did.
Did we?
I remember that.
Well, let's do a proof on the sum of odd integers, and that'll be similar. And if we didn't do all integers, this will work the same. Send me an attendance note, please, while we're here. I'll try to get one at the end of the class also, but send me a ping. And let's make a family of propositions. let's make P of n the proposition that if we add up the first n odd integers, we end up with n squared. So P of 1 is the proposition that if we just add one odd integer, just 1, we end up with 1 squared. P of 2 is the proposition that if you add the first two odd integers, 1 and 3, you get 2 squared. 1 plus 3 equals 4, that seems to work. P3 is the proposition if you add the first three odd integers, 1, 3, and 5, 1 plus 3 is 4, plus 5 is 9, you get 3 squared. That seems to work. So this is an infinite family of propositions which says for any integer n bigger than or equal to 1, the sum of the first n odd integers will be equal to n squared. And we want to prove this using mathematical induction. We want to prove P of n for all n bigger than or equal to 1. So we'll take the approach of an inductive proof. So step 1 is the base case. And here we want to prove P of 1. And since this is just one proposition, we can just write out this proposition and usually see if it's true or not. So P of 1 says 1 is equal to 1 squared, basically. And by looking at this, we can conclude this is true. And we usually don't have to do a whole lot more than that. It's usually just an inspection. Okay, so the second thing we have to do is prove that if P of n is true, then P of n plus 1 is true, where n is some integer bigger than or equal to 1. And we're not allowed to pick a particular n. We can't just set n equal to 5 and show this. We have to show that for any n that we pick bigger than or equal to 1, if this is true, that is true. All right? But we don't have to prove that P of n is true. We don't have to prove that P of n plus 1 is true. We only have to prove if this is true, then that is true. Usually a lot easier than actually proving that this is true. All right. Well, this is an if-then statement, and we've been proving these, for a while now. So let's just start off and see what happens. I'm going to make statement 1 my hypothesis, P of n. Right? That's the hypothesis of the conditional statement. And then I'm going to say what this statement actually says. So P of n is the proposition that the sum of the first n odd integers is equal to n squared. So I'm going to write 1 plus 3 plus ... n odd ints is equal to n squared. All right. Now let me be a little less sloppy with this. Let me put down what the last odd integer is that we're going to add. And this is a bit of trial and error or intuition or something. But if I'm adding one odd integer, the last integer is 1. If I add 2 integers, the last integer is 3. If I add 3 integers, the last integer will be 5. So if I add n integers, what's the form of the last integer going to look like in terms of n? So I'll do my ignore section. Right, so if I add 4 integers, my last odd integer is 7, or 5, or 3. Can we guess? That's close. That's the right form. There's no k involved though. But can we find a formula which turns 4 into 7, 3 into 5, 2 into 3, 1 into 1? So 2n plus 1 looks like it would be 3, 5, 7, 9. N plus 2 Looks like it would be 3, 4, 5, 6. But we're getting really close. Two n minus 1, there we go. Excellent. So 2n minus 1 would be 1, 3, 5, 7. 8 minus 1, 6 minus 1, and so on. So P of n I'm going to write as a proposition that if we add the numbers from 1 up through and including 2n minus 1, we end up with n squared. All right, so we need that leap in our proof here, that thing that we do that basically gets us to where we're trying to go, so that we can just sort of do some legwork to finish it up. We're trying to prove P of n plus 1, and so I need a bigger ignore area over here. So want to prove P of n plus 1. And P of n plus 1 is the proposition that 1 plus 3 plus 5 plus that next to the last odd number plus one more odd number should be equal to n plus 1 squared. Alright, P of n plus 1 would say the sum of the first n plus 1 odd numbers, that's this, that should be equal to, instead of n squared, n plus 1 squared. So I'm going to do something that may seem random, but will eventually seem like sort of an obvious thing to do. I'm going to add 2n plus 1 to both sides of this equality. Alright, so this was definition of P of n. And now I'm just going to add 2n plus 1 to both sides. Right, and my reason for that is just, just something I felt like doing. Add 2n plus 1 to both sides. Well, this is the sum of the first n plus 1 odd integers. And what does this look like? N squared plus 2n plus 1. Can I write that in some different form? Now here's room.
You could write it in a summation?
I could. There we go. Someone said it in chat, right? This turns out to be equal to n plus 1 squared. N squared plus n plus 1 squared. So I can factor this and write it as n plus 1 squared. And so I've shown that the sum of the first n plus 1 odd integers is equal to n plus 1 squared. And that's exactly what P of n plus 1 says. So at that point, I can say, therefore, P of n for all n bigger than or equal to 1, and that's mathematical induction. My reason for 4 was, definition of P of n plus 1. And so we proved a base case, we proved the inductive step, and therefore mathematical induction tells us that P of n is true for all n bigger than or equal to 1. right, it's Friday. It's getting late. We're ready to be done with this. Let me do a very different kind of proof with mathematical induction. So suppose you've got a room with a floor and you want to replace the flooring. You want to tile the floor, right? And you could go out and you could buy a bunch of little square tiles and put them down next to each other and put some grout in between and tile your floor like that. But tiles are expensive, right? So you go to Home Depot and you price out tiles and it's too expensive. And you're walking back to your car and this guy's like, "Psst, come over here. I hear you're interested in tiles." And you're like, "Yeah." And they say, "I'll give you a good deal. I'll give you some discount tiles." So what are discount tiles? Well, instead of being little rectangles, they're little L-shaped things that look like this. That are basically 3 tiles stuck together. So it's a funny shaped tile. And where Home Depot will sell you the tiles you need to cover your floor for $100, this person's going to sell you a box of L-shaped tiles for $15. And you're like, "Yeah, I can afford $15. So you buy this box of L-shaped tiles and you get home and now you're trying to figure out how to use these to cover the floor of your room. And so, I can take 2 of these pieces and I could put them together like this. And I could get a nice little 2x3 area covered. And I could do that twice and I could cover a 3x4 area. And so on. But the question is, can I tile the floor of my room using just these L-shaped pieces? And it turns out that, this kitchen area that you're going to cover, there's exactly 1 tile that has a pipe coming out of the floor. 1 little square that has a pipe coming out of the floor, and you don't want to put a tile there. So you've got your whole floor, and you want to cover it with these L-shaped pieces and tile the entire floor except for 1 square. And the question is, can you do that? And so there's a theorem which says you can cover the floor of a 2 to the n by 2 to the n room with 1 missing spot using L-shaped tiles. Alright, you're not allowed to cut the tiles because you'd have to rent the tile cutter. So you've got these L-shaped tiles, you have to use them intact, you're not allowed to overlap them, and you have to cover every square of your floor except for 1 spot that's missing. And that spot could be anywhere. But the theorem is, as long as your floor is a square and each side has a length that's a power of 2 number of tiles, you can tile the floor. Alright, we got 5 minutes, we got 6 minutes. We can prove this in 6 minutes using mathematical induction. So let P of n be the proposition. You can tile a 2 to the n by 2 to the n room, which has 1 missing square. And we want to prove P of n for all n, let's say, bigger than or equal to 1.
Could you state that 2 to the first, 2 to the n times 2 to the n, if n is divisible by, if n is divisible by 3 on one side and 2 on the other side, if you're going to stack them together, like in that 6 tile thing you just showed.
Yes.
Except for that one spot where there's that pipe in the middle.
So if you had a room that was, you know, some multiple of 3 by 2, yes, then we could definitely tile it, even ignoring, you know, having a missing spot. So there's particular shapes for which we can find a tiling based on something like this, or, you know, maybe stretching it out like this. Right, so we could have a 6 by 2, for example, or some multiple of that. But for a square room, it's not so clear how to do this. And we could, you know, take some of these and put some at an angle and try to build it up, but it's not immediately obvious, I don't think, whether or not we can do this in general. But let's prove that you can. So step 1, we need to have a base case. Prove P of 1. Well, P of 1 is the proposition that if you have a 2 by 2 room, you can tile it with these L-shaped pieces, assuming there's one spot missing. And there's 4 possibilities. If this corner is missing, we take our L-shaped piece and we just plunk it down right here and we're done. If this corner is missing, we take our L-shaped piece like this and we're done. And if this is missing, we put it like that. And if this is missing, we put it like that. So whichever tile is missing, we can see that we can always tile this 2 by 2 room with an L-shaped tile. And so P of 1 is true, just by inspection. Okay, now we have to do the inductive step. The inductive step is usually trickier. We want to prove that P of n implies P of n plus 1. So we're going to assume P of n. That's our hypothesis, and this means that if we have an n by n room, we can tile it with one missing spot. Okay, so I'm going to make a bigger room. I'm going to make a room which is 2 to the n plus 1 in height and 2 to the n plus 1 in width.
So, real quick, just to be clear, so if 1 is missing, can it be literally any one?
It can be any one.
Okay.
Yeah, for this theorem to be true, we have to be able to do this tiling no matter which one piece is missing, no matter where it is.
Okay.
Alright, so I'm going to take my 2 to the n plus 1 room. I'm going to split it into 4 subsections. And now each of these is going to be 2 to the n by 2 to the n. And remember, there's one tile missing somewhere in this room. And let's just suppose, you know, it's missing from right here. Alright, so first of all, I know right away I can tile this section using L-shaped tile pieces in such a way that everything is covered except for this square right here. And how do I know that I can do that? I know I can do that because P of n is true, because that's the hypothesis, and I've already stated P of n is true. And P of n says if you have a room that's 2 to the n by 2 to the n, here's a room that's 2 to the n by 2 to the n, and it's missing one square, I can tile it with L-shaped pieces. So yeah, we proved the base case, so I can totally cover this floor, except for that one tile. So that part's not too bad. Alright, now I'm going to go into this room and I'm going to temporarily ignore this one square in the lower left corner. And so this is a 2 to the n by 2 to the n room with one missing square. P of n says I can tile this. And now I'm going to come into this room and I'm going to ignore this lower right corner. And that's 2 to the n by 2 to the n with a missing tile. The base case says I can tile all of this. And now I'm going to take the upper right corner of this room, ignore that, and P of n says I can tile all of this. And so now I've got my entire room tiled except for this little L-shaped piece, and I take one more tile and I fill it in right here, and I'm done. I've tiled my 2 to the n plus 1 room. So I've proven P of n plus 1, and therefore by mathematical induction, P of n for all n bigger than or equal to 1.
This is just assuming that the pipe is that one square in the middle of the bottom right
Yeah.
quadrant.
Yep.
Will we have a harder time proving this for literally any spot here?
If I put this spot here instead, the proof is identical, right? I tiled this one because it was 2 to the n by 2 to the n with one missing square. And P of n says that square could be anywhere. And then these, I tile exactly the same. But if, my situation starts off and I'm missing a square in here, well, I do the same style proof, right? So I really need to do this 4 times. I need to say if this is the quadrant missing a square, we'll cover this using the base case, and then we'll cover these 3 with a corner missing, and then we'll use an L-shaped piece. So there's some legwork to do. You got to do this 4 times for each of the 4 possibilities where that square is missing, but it's exactly the same procedure, and you end up with the same conclusion, which is P of n plus 1 is true. And then mathematical induction tells us P of n is true for all n bigger than or equal to 1.
Would you accept this drawing as valid justification if we tried to do this on our own?
As long as you did all the words that we did, yeah.
Okay.
And a lot of the examples we're going to do, we're going to be trying to understand the induction part, so we'll be flapping our hands a lot and drawing pictures. We could make this very, very rigorous, but it would be really complex and would really kind of lose sight of the induction part. We'd get bogged down in, how do we describe the position of a hole in the tiling and so on. So we'll do this kind of sort of informal hand-wavy thing a lot over the next few classes to try to understand the induction piece of it. But we're going to tie this into some very real things very soon. So I'm going to leave you with that for now. We're out of time today. But we'll come back, and Monday we'll start off looking at this again, but I'm going to tie it into something else. And then we'll start going through a bunch of examples of induction, seeing how this works and seeing how we can tie it into this other thing I want to talk about. Alright, send me an attendance note please on the way out. Hope you have a fantastic weekend. It's like beautiful out there right now, so hopefully you can get outside or do whatever you like to do. And have a good one, and I will see you on Monday.
Have a great weekend.
Thanks,
Bye.
you too.
And,